Economists' Untold Secrets.
Eradicating Edward Chamberlin's U-curve. The review. Edward Chamberlin's model includes a marginal cost, MC curve, and a U-shaped average total cost, ADC curve. Given a horizontal price line, brought forward from some market equilibrium, a firm produces the output quantity at the point where that line intersects the MC curve. The firm obtains some profit, or loss. If the intersection lies above, or below, the ADC. At the final equilibrium, the intersection happens exactly on the ADC, where the firm earns normal profit. Below are the mathematics for reproducing and clarifying Chamberlin's model. Finding MC. Chamberlin started by looking for the MC curve. This is a standard profit function, where P is output price, Q output quantity, W input price, and L input quantity. Q and L have this production relation. The profit function can also be expressed in terms of Q only. The firm adjusts Q to pursue maximum profit. The last term of this equation is marginal cost. Given P, a firm produces the output quantity until P equals MC. Hence, MC is also a supply function. For example, given alpha equals 0.45, P equals 1 and W equals 0.05, P equals MC leads to the optimal Q equals 6.03. Given P, this equation represents also the marginal profit of each output unit. Maximum profit is then the sum or integral of all marginal profit up to Q star. Don't understand integral? Never mind. Since Q star has been determined, the same profit can be obtained by the product of average profit and Q star. Divide the profit function by Q to obtain average profit, where the last term is average variable cost. The comparison to P equals MC reveals that AVC equals alpha P. Given P equals 1 and alpha equals 0.45, AVC is 45 cents. The firm thus obtains an average profit of 55 cents, or the maximum profit of $3.32. Chamberlin also named this maximum profit normal profit. Finding ADC. Next, Chamberlin introduced plant K for finding ADC. The profit function becomes like this. Because K is fixed, its presence does not affect marginal cost or maximum profit, but affects average profit. Here AFC stands for average fixed cost. For example, given K equals 100, AFC equals 100 divided by 6.03 equals 16.57. When AFC is added to AVC, ATC equals 17.02. The average profit becomes an average loss 1 minus 17.02 equals negative 16.02. The difference between P and ADC will be called Chamberlin profit or loss. Scenarios of Chamberlin profit. Given a normal profit, there are many possibilities for Chamberlin profit. Since ADC is the sum of AVC and AFC, ADC always lies above AVC. Hence, it is impossible to find any Chamberlin profit larger than the normal one. In other words, this Chamberlin profit cannot keep increasing. The largest Chamberlin profit a firm can have is 100% of the normal profit. But that implies K is 0. If the U-curve cuts exactly at the P equals MC intersection, the whole normal profit is annihilated. There is no hanging on. To reiterate, the difference between P and ADC is Chamberlin profit, or loss. Thus, an even higher U-curve will result in a Chamberlin loss, this time without upper limit. When a firm does use some K, Chamberlin profit seems more realistic. But why does economics tolerate two different definitions of profit? The absurdity. While being more realistic, Chamberlin profit can also look ridiculous. For example, how can a firm with 0K produce anything and enjoy the whole normal profit? Normal profit was annihilated, but Chamberlin said that his final equilibrium has normal profit. Why did he say that? He wanted us to believe that his theory conformed to standard economics. Another reason, he didn't know how to measure normal profit. The sequence. A different P equals MC will start a new process, resulting in a new Q star, a new AVC, a new ADC, and a new Chamberlin profit. Since ADC depends on AVC, and AVC on P equals MC, a reverse process as per Chamberlin is impossible. Why did Chamberlin need the reverse process? Chamberlin's different MC. Chamberlin wanted to derive from his ADC curve a different MC curve, that is why he needed the reverse process.
This approach shouldn't be allowed in the first place, but will the MC curve so derived be different from the standard one?
When ADC is multiplied by Q, the result is still total cost in the Chamberlin profit function. The MC so derived is still the standard one. Besides, the minimum of the U-curve and the intersection of the two curves happen at the same quantity. That is, the standard MC curve also cuts the U-curve at the latter's minimum.
Hence, Chamberlin's claim of a different MC curve is redundant.
Furthermore, since MC also represents supply, even a different MC line cannot be drawn erratically. Why did Chamberlin need a different MC curve? Chamberlin's scales. He also called the U-curve scale. Imagined a different scale or U-curve for every increased number of planned. And called the envelope of all U-curves returns to scale, which can be increasing, decreasing or constant. That's why he needed a different MC curve and the reverse process. To justify his scales. However, since K is independent of Q, increasing K does not create any different MC curve. It only creates a different U-curve at a higher point of the same MC curve. As proved, no matter how high K or the U-curve is, the MC line reversely derived is still the standard one. Returns to scale or the envelope that wraps up all U-curves? Gone. Why did Chamberlin need returns to scale? He wanted to find the optimal scale or K. New MC for Chamberlin. A K-dependent production function may have a new MC curve caused by an increased K. But the search for the optimal K kills its fixedness property. Then, there is no more U-curve for Chamberlin to play with. Without scale or its returns, how to find the optimal K? Eradicating Chamberlin's U-curve. Chamberlin's theory is very chaotic, mainly due to one mistake. He recognized K's cost but did not honor its contribution. To honor K's contribution, he should adopt this production function. Since K can be used repeatedly, only its user rental cost should be amortized. Profit maximization results in this supply function. The blue curve illustrates a simulated supply. Divide profit by Q to obtain average profit. The sum beta P plus alpha P is ADC, as shown by the red curve. With this new ADC, Chamberlin's U-curve is eradicated. The significance. The difference between the two curves is Chamberlin's profit, P minus ADC, but it is also normal profit, P minus AVC. Finally, Chamberlin's profit and normal profit are reconciled. From 55 cents and $3.32 respectively in the single input model. The second input reduces the profit per unit to 10 cents, but raises the total profit to the astonishingly $38,742,048.90. Again, every price is brought forward from some market final equilibrium. Temporarily fixed. The new model is just as realistic as Chamberlin's, but resolves all his chaos and highlights K's contribution. Perhaps, Chamberlin's model is still applicable when K is temporarily fixed. For example, a firm with a larger than optimal K earns a less than normal profit. But, that also implies that a firm with a less than optimal K earns a larger than normal profit. That is impossible. The fact is, both too much and too little K reduce profit from its normal or maximum level. As such, Chamberlin's theory has one more shortcoming, being one-sided. Monopolistic competition. Perhaps, Chamberlin model fits only monopolistic competition.
Without any K, a monopolist produces at MR equals MC, prices on a demand curve D, and receives normal as well as extra profit.
With K, the U-curve first reduces and eradicates normal, and then extra profits. If it cuts at the D line, the monopolist has neither normal nor extra profit. A higher U-curve even results in Chamberlin loss. When it causes all the same chaos, the U-curve must also be eradicated from monopolistic competition. Instead, the monopolist should also adapt to this new model.